And again, this is all the materials you need if you want to follow along in the notebooks. This is the coding component. And if you access if you access the repo, you'll have a link to the slides, which will enable you to actually put on links throughout technology. Would anybody mind if I did like a selfie in front of the room? Okay, I keep forgetting to do these things. Raise your hand if it's any problem. No problem. All right, I'm dead. Everyone smile. Yeah.
Hi everyone, thank you for joining us here for the today for the workshop on Langague, a tool of applied NLP. And our speaker here today is Dr. Benjamin Batorsky. He's a senior data scientist at the Institute of Experiential AI at Northeastern University. Please put your hands together for Dr. Benjamin Batorsky.
So I don't know if you got a chance to access this, but if you want, I'll leave this up for 1 second so people can take a picture. You might just want to access the GitHub repo. You'll have the slides up there. You'll be able to get access to code and all that stuff. But yeah, I'll leave that up while I describe myself. I am Batorsky. I am data science lead at the Institute for Experiential AI. Briefly about the Institute for Experiential AI. We are sort of a research and applied institution. We have a bunch of researchers, full-time academic researchers, and faculty attached. I work more on the application side. The solution hub will sort of work with internal and external partners to develop data science capacity and develop actual solutions and proof of concept things. I've been working in data science for a decade, so it's been a while. I've seen a lot of ups and downs and changes and things like that. Basically everywhere that I've worked, and I've worked in a bunch of different capacities, there's been text data available. It's been basically under leveraged. People know that there's insights in there, but they don't really know how to handle it, how to deal with it. So that's been like a major part of my background. And I'm really excited about this stuff because full disclosure, I was an undergrad English major and was super interested in language and linguistics and things like that. And I thought I was just never going to encounter that again for the rest of my career. Funny enough, I'm back. So it's an exciting technology, and I don't know to say it's an exciting time as well. So hopefully everybody's got a chance to access this. Me again. So how I like to always motivate basically every single talk that I give is that basically all the technology that we've seen so far has been because of this massive explosion of technology. People have probably seen this visual before because it's a pretty awesome visual. It's how much data is being generated every minute of every day, and this is updated basically every year, and it gets more and more impressive every year as it goes forward. So just a massive quantity of data is flooding in and empowering all of the kind of technologies that we work with, and also like giving a lot of information that is kind of hard to unlock and insights that might be very useful for a bunch of different applications. A lot of this data is considered unstructured data, and that includes video, that includes images, and text, right? Text I've found to be just absolutely ubiquitous. I said every company kind of has some form of text data, and often it's very hard to unlock anything from that to process it and use the way. So if only there was a set of technologies for processing natural language. But does everybody want to take a crack at this and say, what is natural language? Language you speak? Yeah. Yeah, language that has developed naturally. Yeah, both those are absolutely correct. It's kind of a trick question, I guess. Kind of a circular definition, but essentially you can think of it in opposition to an artificial language like a computer programming language, right? And you can even see the structures are different here, where even in a simple sentence you see there's a lot of complexity, there's a lot of interrelationships between the different words, whereas an artificial language tends to be a lot more straightforward. If then it has a pretty good flow. And it's not talking about probabilistic stuff, but you can see that they're a little bit different. And this is kind of a little bit of a history. I really like this kind of visual from Joachim Goldberg, which gives you kind of the entire history of the field, and particularly puts it on these two axes of how much linguistic expertise, or basically like subject matter expertise, versus machine learning expertise. And you can see that there's been kind of movement towards more machine learning expertise and less linguistics or subject matter expertise, right? We let the machine create a lot of our features. So we had the rule-based systems back in the 1950s. We have a bunch of phrase-based machine translation, corpus-based statistics, sort of powered by the internet and like the just massive flow of data that kind of push that forward. And then kind of a loose machine learning era, which had the advent of neural nets used in language. And then this deep learning era, you could say that it probably is extending even into this time, but we might be entering kind of a new era that's maybe more in the generative kind of world. But this is, I think, a nice way of seeing that, it's not like we've gotten, like everything's gotten better. It's just changed in terms of what our needs, what our dependencies are, and what is being used. And now we can do cool things like this. This is like ancient history now. Like I put together this talk like 6 months ago or something like that, and I had these slides from like a few months before that. This is now like this old, right? This is not even that sophisticated, but very simple plug coding phase staff that you can just give it, I am a data scientist, and it fills it in with stuff that is pretty legible, even though not that interesting. But also ancient history, but all of the different diffusion type models where you can sort of put in a prompt, or like the paired image and text models where you can put in a prompt and it will generate an image for you. And this was, this is just, this is old at this point, right? There's now even more sophistications of these. I always like to put a caveat on these, like, wow, it's amazing, because there's still, these systems are still subject to the data that they are trained on, and so the data has bias, so does the system. So this is some output from DALL-E, and this is old as well, so maybe things have changed, but you don't have to look far for even the latest and greatest models that there is evidence of bias. In this case, you have these different professions that have kind of stereotyped type of people that are represented in them, and it outputs a stereotyped image. Right? It shouldn't be surprising. So, interactive time. What is so text versus structured data? Can somebody give me a sense of what they think is structured data? Sorry. Tabular data. Yeah, I realize when I say structured data, people think more in like terms of the database. But what are the values themselves? Like what kind of when you're talking about structured value data with structured values. Financial data, like a stock ticker. Thank you. That was not a plan. That's perfect. Anything?
Something that you know beforehand.
Yeah, we know how to expect the distribution, right? The examples that I like to go to are height and weight, right? We know that 16 ounces is a pound. We know that 6 feet is greater than 5 feet, stuff like that. You know that there's some kind of intrinsic value measurement to them. Whereas text is a little bit different. Text doesn't necessarily have a comparative value. You can say A is more than B, B and stuff like that. You don't really know how to compare them, right? There needs to be some way of processing it. And additionally, there's all these kinds of, it's not necessarily consistent like a stock ticker, right? It has each state follows the next state. This one comes after this one is a month after that one. You can have a sentence that is, means the same thing, but is arranged in different ways. I like this movie that I like mean roughly the same thing, but they're completely different ordering of terms. So it's complex, and so you need some way of processing it. This is my loose thesis that I'm working on. Welcome feedback on this, but what is the point of natural language processing? I would say is to ensure an accurate response to text, that you are doing something in response to whatever the text data that you have that makes sense. And there might be a use case in which you can read every single thing and respond correctly as at the human level performance. And they're fine, you don't need an NLP system, but in most real world cases, we need some kind of heuristics and automation there. And so the goal of an NLP system, I would say, is to ensure accurate response to an informative representation of input text. And in that case, you need to really focus on what is this informative representation. That's basically the entire talk is going to focus on these informative representations. And then, of course, you need some method of utilizing that representation to do something. We're going to be using a fairly simple sentiment classification use case, but the interesting parts will be happening in the representation area. Not that sentiment analysis is interesting. I have feelings about sentiment analysis. We can talk about it later. So here's the stops on our tour. So you'll notice that ChatGPT is nowhere on here. We're talking about transformers at the end. ChatGPT is not. So I'm assuming people are tired of ChatGPT at this point. Maybe not. But something that I also want to point out is that, I've heard that some of these different eras of NLP are referred to as the prehistoric, the history, right? I disagree with that. I think that, just because you have a drill, you don't throw away your screwdriver, right? There's different tools for different purposes. And, giving away my thesis here at the beginning, but sometimes it makes sense to do incremental things, right? You can do a lot of these tools very simply on your CPU, mess around with it, whatever. And then, once you've found a nice system, then you can sort of build on it. And because I made this talk 6 months ago, this was before, it was a completely different era in NLP at that point. I want to just make a couple more points around that area that this stuff is still relevant. OpenAI and ChatGPT, GPT-4 are not necessarily accessible. It's kind of hard to see what's going on underneath the hood. They're expensive. They're another dependency to build in, and likely just bigger and bigger models aren't going to really make that much progress. It makes more sense to sort of understand what's going on and understand your data, and even OpenAI kind of is on board with that. And a really interesting talk I highly recommend by Jimmy Lin from University of Waterloo. He gave a talk at EAI, and he sort of broke it down that these technologies are not particularly that new and scary, right? They're building on things that have been developing, kind of the awesome semantic search kind of capabilities, and just large language models that have been developing for the last 10 or so years. And I think he broke it down in a really interesting way. There's still this kind of representation application part, even in ChatGPT. I'll try not to mention ChatGPT too many times more. This is the data set we're going to be using. It's a very simple data set. It's small. It's easy to process. It's all that stuff. It has that sentiment analysis, which is a binary. We're going to be focusing on just like a binary positive negative, just because it's a simple application, not necessarily because it's a particularly useful application. But this is the details there. And this is the technology that we'll be using, scikit-learn. Everybody knows and loves it. SpaCy, I like a lot. It's basically like an all-purpose natural language processing library. It has wrappers for Hugging Face transformers and Hugging Face hub and things like that. So it's a cool tool for your general purpose NLP. So we start at the beginning. A token. A token is a useful semantic unit, and essentially that's you take your text and you're breaking it into those useful kind of pieces. A lot of the times I'll just be using kind of white space split, which is just like a split in every white space. And so you can break this up by white spaces. Each individual word can be considered something called a unigram because it's a single token. If you have two tokens together, it's a bigram, 3 tokens, trigram, et cetera, et cetera, et cetera. And it's important to sort of know that this tokenization strategy is happening, even though it's obfuscated away a lot of the times. So GPT uses this byte pair encoding with a sub-word kind of tokenization. And it's making a bunch of choices underneath the hood that you don't necessarily see. And it's important to know, just kind of an aside, I worked with Chinese language corpora, and their tokenization is very different from English tokenization. And it's not necessarily clear what constitutes a token. You can do individual characters, but different characters together mean something very different than the characters themselves. So if you're working outside of the English context, a different tokenization strategy might be relevant. And then, right, so we're starting at bagging and we're going to BERT. So we're going to start really simple and we're going to try and make it. So I use sports metaphors because I don't know, I think that's what we normally do, right? Bagging is essentially what it sounds like, where you're just sort of chopping up your input document and you're just putting it in the bag and everything's kind of out of order and they're just, then you have some interesting characteristics of that bag that you're holding. In this case, we take 2 different documents, we call those different phrases documents, and we put them together into a corpus. And that's a corpus of 2 different documents, and already you have this thing that's called a document term matrix. 2 documents, all the terms for your entire vocabulary. And then you just have 1 instance of everything, so it's 0 or 1. So I would also say that even right here, you have value, right? You can do some interesting things that are actually called NLP. You can call it NLP. I'll implement it. That tell you something about the corpus that you have. Just looking at these 2 documents, you can already see there's a difference between a Patriots fan and a Giants fan. But if you look at a more kind of interesting example, this is actually a term document, so it's transposed. But if you look at all of the Shakespeare plays, you can see some differences here. So, does anybody want to tell me what they see just looking at it, just being the processing, library that they are? There's no fools in history. No, that's an interesting observation. We can discuss that. But yeah, right, you can see the distribution of terms by comedies and histories that are is very different. And so, if your use case was telling the difference, you can maybe even stop here. And to the notebook, we're going to do word counts. Here we go. So if folks struggled with this too much, this is Colab. Apologize, I'm not going to give too much orientation to Colab, but they routinely change things as well. Okay, so we'll be using this mainly because it's easy to share, but also the second part is we'll be using GPUs, and so it's easy to have kind of a low, lightweight, free GPU on this. So you should be able to, if this ever decides to load, you should be able to load this reviews. So what you want to do is you want to upload the review pickle. Yeah, it's the Wi-Fi. Okay, anyway, that's why I have the output here. So you should be able to upload a file. You're going to upload the reviews.pickle.gz. You can also process the raw data yourself with this snippet, but we're going to do stuff with this. We're going to just make a label true, false, if it's positive or not. Yeah, it's on the repository. It's bagging to BERT. If you look at bagging to BERT, I don't think there's another bagging to BERT. My GitHub username is BT, then you should be able to find it. I'll put this back up for a brief second. So this is what you want BT bagging to BERT, and you should have all of that. Okay, I'm gonna move on. Sorry, didn't do that. Didn't get a picture. Yeah, and I apologize. I know the Wi-Fi is a little bit tricky, but you'll load this in. You'll just process the label just so it's easier to deal with, and then we can just look at the data. Right, that's a good thing to do. Look at your data. You can look at an example of a positive and negative review. Yes, it's just paragraphs of text. It's you can just look at this. It's kind of hard to tell. You don't see like, oh, this movie is terrible, blah blah blah. It's kind of hard to tell what is positive and negative, but these have been labeled by like annotators. So we're going to trust that they're positive or negative. Something that you can do kind of like right out of the box is that base Python just has this counter object, and you can essentially create a term count. This is white space with that. That's not particularly efficient or that useful, so you can just use scikit-learn as a count vectorizer, which basically does that work for you. And it's pretty performant and output this sparse matrix. Sparse matrix kind of makes sense because if you have a bunch of documents together, there's going to be words that appear in one and no other document and things like that, so it makes sense to store it in a sparse structure. But yeah, it sort of does the word counting thing for you. And then you can call, what I do is I'm just trying to make this look like the counter, so we can look at these two different things, and can anyone tell me what's the difference between this, or some differences between this one? Right, yeah, the data type should, yeah. But more like what are the, if you're looking at the counts of the individual terms, what are the, if you see any differences? Oh, yeah. I didn't think about that, yeah, there's also such a, yeah, in fact, oh, this is really hard to see, okay, yeah. Okay, can't see. Is that visible? A little better. It's hard to see. Yes, some words were removed. They were like single character words, but the basic point is there's also lowercasing done here. So there's a bunch of processing that by default scikit-learn make into it. And the only thing I reason I point that out is because it's surprised me before, so hopefully it doesn't surprise other people. But it's interesting. It's good to know what are the decisions being made under the hood of your system. So I always like to do this. I'm like just an absolute advocate of doing some kind of deterministic approach. This is kind of a dumb one where we're just having a label, like a set of positive words, a set of negative words, and we're just saying, fit a threshold to those counts and on the training set and apply it to the test set, and see how that performs in terms of the classification. And we just picked a kind of random set of positive and negative words, and then we're just going to apply that. It takes longer than probably should. Oh, I shouldn't have done that. Never mind, because it's not actually okay. So the output, I'm going to spoil the output here. It's really bad, which is not too surprising, but this gives you a good baseline, somewhere to build off. So let's actually do the word counts, right? We said we're going to do word counts. And so in this case, I'm using scikit-learn's pipelines. Again, I'm not going to describe how that works. But essentially, you can think of it as the things that I sort of set up before, where it's creating a representation and then creating some way of using that representation to do something that makes a choice. So we're just using a simple logistic regression, nothing fancy. So when we run that, we get, we can fit it to the training set and test it on the test set. And then we're going to be looking at these classification reports for the rest of the time. And we can see it does pretty well, I would say. Kind of out of the box without there being much more additional work. Something that you should note is that, here, I didn't mention this, I'm removing stop words, which are words that are like be and but, things that add not much more additional information, and then restricting the number of terms to ones that appear in at least 1% of all the documents.
What is the true and false there? I think it is.
Oh yeah, sorry about that. Yeah, I should have changed this. So true is positive or false is not positive, right?
Different document, say if the document is positive or negative.
Yeah, yes, yeah, positive or yeah. It's the only two, like the raw data has pos and neg as the labels. I just made it it's not equal to pos, it's false. I know this, sorry, I should have kept it in, but whatever. But yeah, this does pretty well. It has about 1,500 features. So that's the only caveat, right? There's a ton of features that it's learning from. And yes, so we'll actually see, this is a spoiler, we'll actually see that this is a pretty good performance, like across the board, right? Like, it's gonna be hard to beat this performance. And one of the things is because it has so many features and because it's kind of fit to the data set that it's actually looking at, and it doesn't generalize well. But it's still worth noting that a very simple approach can do pretty well in a constrained setting. Cool. Does that all make sense? I know I've been like flying through this. So. Great. We're going to move right along. So let's get to, so this is our progress so far. Term deterministic does really bad. Word count does pretty good. So I said that point of NLP is a great informative representation of text. And right now we have these word counts and they're sort of like everything's sort of being counted the same. We have a bunch of different forms of like, I am and I will, technically sort of mean similar things. We have a bunch of stop words, or actually we kind of split those out. But one approach that might make these representations more informative is to create kind of a weighting regimen that we know that certain words are more informative than other words, rather than just completely cutting them out. And that is the idea behind the TF-IDF strategy, weighting strategy. And it's just term frequencies, which you've already seen, those are just the word counts. And then inverse document frequency. The idea is that a word that is pretty common across your entire corpus is not that informative. Think of the, it appears in basically every single one, not very informative. So if it is a very common term, it's going to have a high document frequency, and if you invert that, it's going to have a low IDF. So the weight is going to be low. So it's going to be downweighted as opposed to one that's more uncommon and particularly exclusive, more exclusive to the document that you see in it. And so it's going to get upweighted in that representation. Yeah, and so you multiply the term frequency by the inverse document frequency. You can sort of see in that Patriots and Giants example that you know that the word Patriots and Giants are probably the most informative things about those documents. And if we apply this kind of simplistic version of the TF-IDF, the word fan, which appears in both documents, gets downweighted. Patriots and Giants stays the same. Very simple stuff. But it actually works pretty well in terms of giving us characteristics that we kind of like. We know that there is a difference between a Patriots fan and a Giants fan, but with the count vector, they look pretty similar if you just compute a cosine similarity. But if you apply this weighting, they look less similar. And so that seems like it gives us a property that we like. We go back to the notebooks here. Yeah, I know everything's disconnected. And we have an example here, which is just the movie was good, bad, great, and it's sort of the same thing as I was saying in the other example, where the words bad, good, and great are more informative about the documents, and they get, with this term frequency weighting, they get higher weight than the ones that And again, we're just going to use essentially the same pipeline structure. Instead of the count vectorizer, we're going to use the TF-IDF vectorizer, which also exists in scikit-learn, and we're going to get the same performance. It's you know, in this particular use case where you're doing classification, maybe it doesn't matter that much. It's an easy thing to implement and switch around so you can always see what you get. And it's also kind of interesting. I have some explorations here of what are the differences, like how does a prediction differ, like what one predicts as positive, one predicts as negative. I have this kind of overwrought example of essentially ranking the coefficients on the lizard regression fit to TF-IDF in the count vector. And upshot is essentially words like bad have much more higher magnitude. The model is learning a lot more from instances of the word bad in the TF-IDF representation than in the count vector representation, which seems like a property that we like, because that makes sense. That's just one way of looking at it, just to justify that it wasn't a total waste of time to go down this TF-IDF area. Yeah, some examples of differences and things like that. What do we think? TF-IDF? Make sense? Cool. I'll take that. Great. So this is our progress so far. We haven't really moved too far. Now, something I want to bring up and justify the next sort of method is recursive dimensionality. Anyone give us a quick definition of that? Data scientists love this.
Too many features.
Too many features, yes. You have too many dimensions, right? And that leads to overfitting, it leads to a bunch of different, bad statistical properties. And we have 1,500 features, even with some cutoff in the count vectors. If we start adding more and more documents, we might see more and more, a larger and larger vocabulary, and so we start getting into this problem. And again, our point is to get an informative representation of the documents. So if we just start having huge sparse vectors for every single document, we lose, there's not that much information added by these additional dimensions. Oh, wait, I spoiled it. How do we address too many dimensions?
Yeah.
PCA, dimensionality reduction, we all love this. And basically PCA, or dimensionality reduction, oh gosh, everything's this name. Dimensionality reduction techniques are often referred to as essentially topic models in this NLP kind of context. The idea is that they're just tools to discover the main themes, kind of decompose the word counts into something that is, captures some kind of theme in your corpus. And so the theory here is essentially the document is functioning with topics, the topics are functioning with words. So if you think of like the probabilistic idea behind LDA, essentially it's, if you sample from a topic distribution, you would get a certain distribution over words, and that would essentially recreate your document. And it's a similar idea where essentially you want to reduce the dimensions without losing too much information. And this is just a visualization of it. I work in a nice visual way. You can think that these two dimensions are like, word counts or something like that. The vocabulary of two. This is all your documents spread across that. And you can very clearly see where the axes of variation are there. And in 2 dimensions, the 2 dimensions is not that exciting, but you can imagine this across, 1,500 dimensional vector. It's a little bit more interesting. I also have a motivating example. This is from my previous work that I did, where it's essentially categorizing small and mid-sized businesses. They sort of straddle a bunch of different categories. And so it would be useful to say, like, how much are they, in this example, yoga studio or cafe or retail, how much do they sort of fall into each of those categories? And you can use this sort of text from the website to kind of understand that. So that's the customer's own words, or sorry, the business's own words. And so you can sort of understand them through that. This example is a video is no longer with us, but is, I think, a good example. And what's really nice about talking about this, and what's really nice about this use case, is that it was very easy to get people on board because it's very transparent. It's a little bit more of an art to figure out what these different topics really mean, but they're a little bit more legible to somebody that's maybe not as technical. And so I really like this visualization. This is the loading of each individual word on each individual topic. You can think of the relevance of the word to that particular topic. You have 3 topics here. Can anyone name like the blue topic? What do they see? Topic 1. University education. Yeah, exactly. And what about 3? Food and restaurants, yeah. I mean, I guess I kind of spoiled it by putting it right there. But it's pretty easy to see, and you can put that in front of anybody, and they can kind of see that that's the case. I mean, with the caveat, right, like we're sort of top level doesn't give you those like descriptions, it just gives you what is the word loading on these different things, and you're applying it. So different people's views might mean something different, but it's a useful tool all the same. So now we're going to do something fairly simple with topic models. I have this little utility function just to show the relevance or the loading of each word on those different topics. I just picked 10 topics just because I'm using non-negative matrix factorization because it gives each document a sort of a blend positive loading of each document on these different topics. I'm using TF-IDF as the TF-IDF representation goes into the topic model. The topic model creates a n-dimensional representation for across all of the different topics. And these are the topics that we get out and the most representative, the 5 most representative words. Anybody see anything here? Anybody like want to try and name one of these topics? Maybe, I guess, top number 7. Sorry, I heard something back there. These are the top 5 words for each topic, yeah.
So you got some horror movies there.
Yeah, so it's sort of like a horror aspect
Yeah.
of the movies that are being represented. And, you know, if we just look at that, is that necessarily the case? We just take a couple of them that have very high loadings on that topic, and yes, they are reviews for horror movies. Not to say that's going to be like a kind of cherry pick, right? The ones that are most the highest loading on those topics, but it's useful just to kind of look at. And so we're going to do the same thing. We're going to do a pipeline TF-IDF to non-negative matrix factorization to logistic regression, and the result is it's worse. So we're going from 1,500 dimensions to 10. If it was not worse, I think something would have been wrong. But we already saw that there's some like intuitive explanation for some of these different topics, and you can see yourself manipulating them a little bit, creating a little bit more interesting features out of that because something to work with, and something maybe for people to look into that may not be as technical. Yeah, and I have an example here where I also add some TF-IDF features as well, and you can see, you know, it boosted the performance, but that's not too surprising. All make sense? Still fairly simple. Don't worry, we're gonna get deep soon. All right, let's do it. Let's go for it. So this is our progress so far. So your topic models work on your current data set. They describe it pretty well, right? Your decomposition. But what if you get new data and it's completely different, then all of a sudden your topics have nothing to do with what you're seeing. And so what might make sense in that case is to, like, it would be great if, for example, you could get like all of the text that you're likely to see and generate some general topics of all text, right? And have some characteristics, have that knowledge kind of built into your next learning system. And lo and behold, that's the idea behind transfer learning. And transfer learning is huge and complex and all that stuff. And, you know, not going to do it justice in one slide. But I really like this visual because I think it breaks it down very clearly in kind of just a traditional setup. You might just take a task and you have your learning system learn on that task and have 3 separate tasks. But in this transfer learning setup, you might have a source task that generates essentially like knowledge patterns that are useful for your target task that you can sort of push into your learning system and do a better job on your target task. This is roughly the idea of transfer learning. And basically everything that we're going to be doing, not everything we're doing, some of the things that we're going to be doing, and a lot of the work that's done in NLP now uses that idea of transfer learning, that we can take a model that's trained kind of separately from our objective and use it for our objective. And one like kind of simplistic example of that is like a source task of taking term co-occurrence statistics, just stats around how often two words appear together. And I like this example. This is a term matrix, so it's how often the two terms, how many documents the two terms, it's how many times the two terms appear together across one of the documents. 10 times, yeah, that's what it is. And so just looking at this, right, we are all sophisticated processing technology ourselves. What does this sort of tell you about pi and cherry versus pi and digital? Sorry, somebody said something I couldn't hear.
Pi and cherry are highly correlated.
Yeah, exactly. There's a stronger relationship between pi and cherry versus pi and digital. And you can maybe argue that has something to do with meaning. It might, but it's just there's some relationship there that gives us some understanding about what the how they're connected. And you don't see pi and digital together too much unless you're working in like Raspberry Pi or something like that. So that idea, what we're seeing right here, is essentially the concept behind word-to-vec and glove, which is based essentially on those sort of co-occurrence statistics. That you can sort of know a word by its properties alongside other words. And I know word embeddings are ancient history, we've bored of those right now, but I think they're still super fascinating in that just from a fairly simple concept of just co-occurrence, we get some interesting properties in terms of what their representation looks like in space and in relationship to other words. And also, I argue that a lot of the latest technology is based on co-occurrence, right? Co-location. There's a ton of really interesting properties that come when you use enough co-location and enough data and get some really cool results. Such as this example from a really interesting talk on embeddings for a job description. This is a TC two-dimensional representation of word embeddings from job descriptions. And you can sort of see, I just highlighted, or the speaker highlighted 2 areas here. Does anybody want to take a stab at what one of these areas are? Red or blue? Sorry? Yeah, skills, job skills and things like that, exactly. Yeah, this one seems like it's, your requirements or prerequisites. Yeah. So it has some cool things there. This is also a really cool example, right? I always want to caveat like bias in the data leads to bias in the model. And this actually shows that that bias kind of tracks with historical patterns, right? And so there was, I'm not going to explain the whole paper. It's a really interesting paper, an interesting read, but basically there's bias in these word embeddings. If you train them on text from particular eras, you see that sort of gendered bias exists, and you start seeing the correlation between eras kind of break around the time that there was like active women's rights movements, at least in the US, during that era, and you can see that the correlation breaks. So it's interesting, like there is bias in these data, and that's represented in the embeddings, and it's even so clear that you can like track history a little bit with that. Cool. So now I'm going to introduce Spacey, and Spacey's documents are awesome, and they do a much better job of explaining themselves than I do, but I'll give you a very light touch. Essentially, everything is organized around this kind of language pipeline, language model, which has a bunch of different components, including like tokenizers, including tagging models, named entity recognition, a bunch of different stuff goes on. You can train those different components, you can swap them out, you can take pre-trained components. There's a bunch of different modularity in this. And essentially the idea is it'll will take raw text, it'll turn it into a spacey document. Those documents are composed of multi-token spans, and then there's individual tokens, and each of them have the different attributes like part of speech and categories and things like that. We're going to be focusing on, you can get like categories, like a category pipeline on this, and we're also going to be using the vectors that we can just sort of shove in the pre-trained glove embeddings, which we'll be using in the next example. Cool, thumbs up. Oh, is there a question about?
No, thumbs up.
Okay, that was a thumbs up, sorry. Glasses. Great, so word vectors. So you can support spacey. You'll need to do this on Colab. You'll need to download a Medium web model because it has glove. And then if you just use the base model, it won't have that. So once you just install that, you should be able to load it this way, where you just spacey up. And then right here, you have a spacey language model, essentially. This function is just, I created a way of using glove vectors in our pipeline. The idea is I'm just taking the average of all of the word embeddings or level embeddings for a particular document. I'm taking that as the document level representations. Remember, these word embeddings are at the individual word level, and we want a document level representation. So this is kind of a hacky way of doing it, but it's a way of doing it. What's a better way of doing it? It depends, right? Like, you might want to like concatenate different things together, but then you have to have you don't want to have like because each of these embeddings are 300 dimensions, and if you had every word, it would just not really work. I don't know, there's probably a better way. You can experiment with it, right? Maybe take the maximum or something like that of these different dimensions. You know, it's your results may vary. Good question. And so we're doing the same thing. We just our preprocessor, our representation part is going to be based on that document level embedding. And the results are not as good as our word count, but again, we're doing this is 300 dimensions versus 1500. I'd say that's still pretty good for a reduction of like fit, right? That's for fit with features. I'd say that's still pretty impressive. And right, this is with no additional tuning, no additional like messing with it. I still have, this. I haven't reduced the number of terms. Still 1,500 terms that are being represented in the layer that goes into the glove embeddings. So, yeah. How does that sound? Does it make sense? All that? Cool, great. So we'll move right along. Where are we at? All right, we're going to move a little bit quicker. So here's where we're at so far. I'm just going to spoil this. So this is a joke. Every presentation needs a joke. And this is funny mainly because of the context that's around it. That well is a condition, but also a thing, like the wishing well. Let's just make a point. The context is everything in language, right? And right now, everything we've done so far is just totally context independent. We've essentially chopped everything into our bag, right? And it has no real connection to each other. Word to that, arguably, with the glove, has some knowledge in general context, but in the context that we're seeing it in our documents, it doesn't, right? So if it said well, the embedding for well is there's one embedding for well. And it's independent of whether it's wishing well or doing well. You can do a bunch of things like, handcraft your own bespoke context, and that's valid, right? This is a valid strategy for incorporating context, and it might actually work perfectly well for you. But it takes time, it takes tuning, and it takes, we're data scientists, we don't have time for that. And so we can just trust the machine. That's what I would say that these deep learning models are doing. They're sort of incorporating in this particular context. They're incorporating some aspect of context that is sort of hidden behind all of the layers that are there. And explaining RNNs and CNNs in one slide is going to be complicated and difficult, but the idea is that and what I'm trying to convey here is that both architectures incorporate context, and that's sort of what gives them kind of power over some of the ones that are context, not context sensitive. RNN will scan over the sequence, and each hidden state will contain some information about the previous hidden state, depending on the architecture, have different directions, things like that. Convolutional neural nets have context in that they have their sort of receptive fields that scan over the document as it sort of evolves. And so I'm trying to articulate that with colorful balls, and hopefully that kind of makes sense. They're doing sort of the same sort of thing. And so this is the CNN. We're going to start with the CNN, and this is just kind of a default text categorization pipeline that is in Spacey. It works pretty well, so they've kind of made it their just standard one. And so you have the input, which is these different tokens. They are embedded based on some certain properties of the word itself, and into these hash tables. Those embeddings then go into a multi-layer convolutional neural net that includes, a window around each token, and because it's multiple layers, you get kind of a wider context. And then that just passes into a fully connected neural net. You can think of a fully connected neural net for simplicity as just like logistic regression, right? It's making a classification on top of what comes out of the CNN. Spacey uses the word embed and code. So embedding is this hash tables, and encode is this CNN. It's pretty conceptually simple. And the way you sort of set up these architectures are in these config files that Spacey has. And the configuration is for the language model you're using. So that little NLP is one that we had before, the little web, the medium-sized web model. It has its own configuration file behind it. It has its own like structure like this. We're going to just be setting up essentially their default here. You can see that in the components section. We set up. This is a simplified version of the config file. The config file is in the repo, so you'll be able to see it. What I want to say about this. So the pipeline just has its text categorization component, and we're defining the model that underlies that text categorization as the text cat CNN class. And then within that model, we have something that takes tokens and turns them into vectors. That component itself has embedding. And then the encode part is the CNN. I know I just kind of flew through that, but I think it's fairly straightforward. You can sort of see in the config file how it's sort of laid out, and that visual that we had before, you can just sort of see where these pieces are located in the config file. Great. So now we're actually on part 2 of the tutorial notebook. I think we're still good. Great. We're in part 2 of the tutorial, and it has some of the similar kind of things up front. I added a little bit about mounting your Google Drive to the notebook. I was just using it because it was easier than like restarting the lab and re-uploading everything. You don't have to do this, but if you say take my Google Drive folder and you put it in your own drive, you can do this. It might be easier for you to get. Also in the Google Drive folder is some pre-trained, or some ones that I trained, some the CNN and a transformer model that I trained, and so you can get those and play around with those as well. So you want to also get the repository itself, own repository to your collab as well, because you'll need the configuration files particularly. This pre-processing function is essentially just turning our corpus into something that Spacey likes. Spacey likes these document objects that are smaller and optimized for use in Spacey. You don't have to do this, but you have to change the data reader to not expect a document object. Not use it. This should give you what you need, and it will save. Once you run this, it'll save a train.spacey and test.spacey. So I realize I also have this open over here. Ignore all the crap that's in here. Yeah, you should be able to see, you won't see all of this stuff, but you will see these 2 files here. And what I also want to show you is in the Spacey materials, there is a configuration file, which is what we were seeing on the screen before, plus a bunch of other information about how it's going to do the training. So that'll exist. Great, and so now we're just going to use Spacey's own kind of training function. We're going to give it that configuration file. We're going to give it out the path. We're going to tell it where to look for the training and the dev set. And I feel like I have to always put this disclaimer. I always have an ambition to like split things into the train and the dev and the test set. I never do. But always make sure that you have those 3 splits when you're doing development on the model, and then just have the final evaluation on the test set. But don't do it, want to do it. I just have this training for 1 epoch, and I'm using the GPU. So something that you should notice, I should have mentioned this up front. When you open this part 2 tutorial notebook, if you go to runtime and you go to change runtime type, you should see that it's using GPU. And you want to be using the GPU just because it's going to be faster. The CPU can train without the GPU. The CNN can train with the CPU. The transformer is going to choke. Let's see. So this is what it'll look like. You'll start seeing this training happening. You'll start seeing the loss on the text cat component and the cat score, the scores, the same thing. And we'll just train, depending on your parameters. It might stop if it doesn't find any, if it doesn't improve after a little while. But this should just train for 1 epoch. And then you'll be able to essentially load your own model. So we put the output path as CNN model. And so what we want to use is you can load, so right here I have this as the loading the trained CNN that I had, that I trained for multiple epochs. Your model, once you finish training it, will be located here in the CNN model, and you'll take the model test. And you can use Spacey's own evaluate function, or you can just load it and use it as you would with any other Spacey model. Fortunately, I don't know if this thing is all disconnected. I apologize for that. But I mean, the upshot here is that you're going to see cats. It's going to give you positive and negative, or sorry, it's going to give you true and false. And true is going to be, whether it's positive and false, it means it's negative. You're going to see much higher probability for this particular document. That the categorization is very likely positive, which makes sense. And shoot, I don't have the classification report here. It's a shame. But the upshot of this is that the performance is not better than our word count. It's basically it's comparable to the word spec, but that's fair because this is after training for 5 epochs. You can train for longer. You can change the parameters to provincial tuning, and I'm sure you can get higher than that, but not necessarily you would need the word count itself. So let's move on a little bit further. So one of the things that RNN and CNN struggle with is long-term dependencies. We talked about that before a little bit, where it's like, this movie that I saw yesterday was bad, right? And so to be able to actually get the connection between movie and bad, you have to have context from basically the entire sequence. Very hard. It's something that there's a lot of architectures that were attempting to get at this problem, but one that actually kind of solved this problem well, addressed this problem, was giving the architecture the capacity to draw connections between words across the entire sequence. And that is essentially what attention looks like in language. So you can imagine if you are all expert natural language processors, you know that there's connections between these different words. And so you sort of know that in the expression, I watched a movie today, that the I is doing the watching, the watching is happening today. You have all those connections. If you give the architecture the ability to draw those kinds of connections, it can do some really powerful things. And this is just a visualization of the attention weight, so the weight between different words that happens underneath the hood of a model that has this attention mechanism, and you can see that there's like a pretty strong connection between eye and watched. Yeah, and it's a bunch of different, a movie, right? A movie is like essentially one noun chunk, and so it's a strong connection between those. Not necessarily that it knows those same kinds of relationships, but it has the capacity to learn the relationships, interrelationships between words across the entire sentence. This is self-attention predictive. And that brings us to our like kind of last, well, second to last architecture, which is a transformer model, which essentially just really leverages this attention mechanism. And I tried to use color balls again here. You know, this is going to be hard to explain in like a very short amount of time, but essentially there's these two components to this architecture, an encoder and a decoder. And one way to think about it is with our PCA example, right? We have this, all this data, we collapse it down to these different dimensions, and essentially imagine we're taking those dimensions and trying to reconstruct the data again. So an encoding and a decoding. That's a really simplistic way of saying it. It's more complicated, there's different properties there, but that's a way that you can think about it. And essentially every single token gets some information from the entire sequence because of that ability to draw those connections between the different points because of the attention weights. And the encoder passes all that information to the decoder. In this example, what we're trying to do is predict the next word with this machine. And you know, we can imagine that it's already predicted what, it's already predicted time, and now it's on that third step trying to predict what's next. It'll take everything that comes from the encoder, it'll take what it's predicted so far, and do a prediction. Transformers, this is you know, ChatGPT. We all understand ChatGPT, we're all experts now. So one thing I'm pointing out with that decoder part is that it's autoregressive, that it only sees its past, it doesn't see the future. Because if it sees the future, it basically knows what its objective is and it's cheap, right? Ignore everything else that it gets. But you can imagine there's an advantage to being able to look at the whole sequence like the encoder does in doing the predictions for what that word, what the missing word is. And that is essentially what BERT is. We've sliced off the decoder. We're just using the encoder, and how we deal with that cheating problem is we're just masking certain tokens. So it sees the entire sequence and tries to predict that one token that is missing based on that context. So that gives it a lot of power for a lot of different tasks. And again, we're using the transfer learning framework here. So this is actually like of the Google BERT model that you can just download off Hugging Face, has been trained for a long time. It's a ton of different parameters. It'd be very expensive and difficult for you to train yourself, but it has been trained on this task of predicting massive words. So it has internalized some patterns of language that make it very useful for downstream tasks. And then the example that we have here is just going to be fine-tuning it for our purpose. I think I have. So yes, described all of an entire like aspect of NLP in a couple of slides. Hopefully that wasn't too whirlwind. What we're going to do in Spacey is essentially use the same kind of setup where we're going to have our input, but in this case, instead of doing the hash embeddings and the CNN on top of it, we're going to use the transformer. We're going to sort of plug in a pre-trained transformer. And that's that transformer component. Then there's this new component called listener, which essentially just takes the output of the transformer and reconfigures it so it lines up better with the tokens that Spacey has been using and expects, and then passes that to the fully connected layer. Pretty simple. And like, one of the things I like about Spacey is that you can sort of mess around and like swap out different components and try this transformer, try this CNN, try a non-deep approach, heaven forbid. But the configuration file doesn't look all that much different. We still have the components. We have a new pipeline component, which is the transformer. And in this case, our model has a toke-to-vec component that is a transformer listener, which waits for the output of the transformer. We define that transformer and we define the model as basically anything from Hugging Face. Because it's Spacey transformers is just a wrapping on top of Hugging Face transformers. And so in this case, we're actually pulling in a smaller version of BERT that has been fine-tuned for sentiment analysis. So as close to what we want to do as possible. Yeah, go ahead.
Yeah, can you briefly, I don't know, can you briefly explain the statement, attention is all you need in the context of what we're doing?
Oh my gosh. I don't know, I feel like the paper does a much better job of it, but it's just,
If you can't, that's fine.
I mean, I would say, like, briefly, it's just a really powerful mechanism for, like, doing those things that we know exist in language, connections between different words and long-term dependencies and stuff like that. You're giving the architecture the ability to learn something. Whether it's learning exactly what you expect is a whole other conversation, but it now has the capacity to do that.
But in terms of like the diagrams, attention is all you need, what you just say, it's just, what they're arguing is, the transformer is all you need. If you don't talk, right? Isn't that essentially what you're saying?
Well, I mean, I guess we can talk about this, yeah, I mean, I feel like this is a deeper conversation, but I think it's a attention-grabbing headline or something like attention-grabbing title, but it's just showing how effective this mechanism, like just as a architecture built around this mechanism, attention mechanism. Yeah, good question. Right, and so that's it. Like this is the last piece. So you can also use a sentiment analysis pipeline from Hugging Face from Transformers itself, which does pretty good. I forgot exactly what the classification report does, but it's actually like better than CNN. And it's just this kind of the out of the box sentiment pipeline that they have. But we can also sort of fine tune on our data set itself. And in this case, you're going to be using the config _ TRF for training, for fine tuning this transformer model. And everything else sort of proceeds along the same. This will take a little bit longer than the CNN, just because it's bigger and sometimes Colab might complain. But the output is actually pretty good. So I'll make a note here. So I'm just subsetting it to 500 because at one point I was able to do this live. And it takes a little bit of time and sometimes a lot of times out if you try to do a larger set than this. But it actually, for a subset of data, it performs better than word count without really much additional like tuning or tweaking at all. So that is the whole tour. The things that I would say is that if you still look at this table, I know the word count to some extent is overfit to the use case, but the difference between the word count and the really advanced models is not so drastic. And I would argue that you could probably, with fairly simple methods, get 80% of the way to your goal. And then, once you've established that that goal makes sense, that system is actually, supportable by your engineers, then maybe you can be like, well, what if we did more? Right? What if we added a GPT on top of it or something like that? Right? And so that's my kind of end advice. You start simple and you add complexity. You might want to mess around with these like kind of older tools because they're very easy to mess with. They're kind of a little bit more transparent. You can see, for example, you have some weird HTML in your data or something like that. So it's easier to detect that if you're actually, doing a little bit, some of the things by hand. Word embeddings are still pretty powerful and pretty useful. And then you can add a little bit more context with, maybe even hand curation, but also you can bring in like bigger guns like BERT and GPT. And these are all informative representations, right? I sort of dropped the thesis a little bit, but all these things give you a representation at the word level, document level, whatever it is. And then it's up to you to figure out how you take that representation and do something with it. On the different use cases, right? This is not by no means comprehensive, but we've been doing like classification, right? We could do things like similarity between documents, sequence hacking, language generation, which is everything now. And that's everything. Here's some more resources. Thank you very much. Thanks ODSC for having this exciting conference. Love coming here. Thanks everyone for attending. Anybody has questions? I'll just go everybody's hungry. Oh, there's a question. Yeah, I don't know. It's gonna be hard, there's a mic up there, I don't know if that's. Yeah, okay, I mean, I guess if there's no